Okay, greetings. I am not here today, so I'm going to be kind of walking you through the notes for your polar equations. So polar equations are definitely useful when you get to BC Calculus in the spring semester, and we're going to be kind of going through them together today on your calculator. So just remember that rectangular coordinates are of the form xy, while polar coordinates are of the form r theta. So you've got rectangular and polar for those first two blanks. And although there's a bunch of different types of polar graphs, just like in the graphs that you've been working with in Algebra 2, etc., you know, there are lines, there's quadratics, there's cubics. Well, very similarly in polar, there's a bunch of different types of graphs, but the ones we're going to focus on today are circles, rose curves, and lemniscence. Okay, that's a French word. So we'll kind of start with circles. These are all going to be examples of circles. And what you can do is you can kind of graph them in your calculator. So I'm going to kind of insert the calculator here. And remember when you're graphing these that your calculator needs to be in polar mode. So you turn your calculator on, you hit the mode button, and you go down. And so you arrow over here, so the POL, you need to hit enter so that that part's highlighted right there. And then you're going to be good to go there. Okay, so quit. Now notice when you hit your y equals button, instead of it being y equals in there, now it's r. So just like we had said above that polar coordinates are of the form r comma theta, that makes sense in here because now we have an r. So now we can type this in, r equals 4 cosine theta, so you just type it in as r for cos theta. Notice now that when you hit that x button, it actually activates the theta right there. And when you graph it, I hit zoom 6, you get this. If you wanted to zoom in, you could. Because it's a circle, another handy thing is when you hit zoom, if you actually do square, it's option 5. That'll make it look a little bit more like a circle, and I'm going to zoom in on that so that then you can kind of see it. Okay? And you could play around. You can adjust your window. Notice in your window here that my theta is going from 0 to 360, so that means I am using, I'm in degree mode. I'm going all the way to 360 degrees. That t-step, how quickly is theta counting? My x-max, I'm going to make my x-max just a little bit bigger so that I could see the whole thing. All right, and there you have a circle there. So if you were making some observations about this, I would say that this circle looks like it has a diameter of 1, 2, 3, 4. Okay. So this is a circle with a diameter of 4. And notice that it is all the way to the right-hand side of the y-axis. So the entire circle is to the side or the right-hand side of the y-axis. Okay. So right now I want you to pause the video, go ahead and try to graph these other 4 examples. You can sketch a curve on your paper and then see if you can get it to match. After you kind of graph them, try to see if you would be able to fill in the blanks right here and see what those different things have, what changes that they make on the graph. Okay, so go ahead and pause. Okay, so hopefully you went ahead and graphed those in your calculator and you got graphs that look like this. Some things that you might start to notice is that this number out front, right, seems to have a direct correlation with the length of the diameter of the circle. Okay, so some other observations you may have noticed is that the ones that had cosine were either to the right or left of the y-axis, and notice it was to the left when it was negative, and the ones that had sine were above or below the x-axis, depending if that number in front was negative. So hopefully you kind of made those observations there. And if we were filling in the blanks, it says r equals a cos theta is a circle where which one of those numbers is the diameter? Well, it was the A was the diameter. So A is the diameter of the circle that has its, well, when it was a cosine, its leftmost edge, right, was at the polar origin. Notice, though, when A was negative, right, so a negative coefficient will flip, okay, the graph over the axis. Flip the graph over And I'm just going to say axis because notice that if it was a sine graph, it'd flip it over the x-axis, and if it was a cosine graph, it would flip it over the y-axis, or the y-axis. Okay, and notice when it was a sine, A was still the diameter, okay, and its bottom was at its, bottommost edge was it there. So this is an example, and then we noticed that when that became a negative, then it was the top. It kind of flipped it over. So those are some conclusions that we can make about circles. Circles are kind of the easiest one, and notice though that with the circles there was no coefficient with the theta. Notice that these thetas were all by themselves, so that's an important observation in how you get a circle. Okay? All right. So next up, we have rose curves. These are really pretty. They look like flowers. That's why they're called rose curves. Okay. So it says sketch each of the following using your calculator, then make some conclusions. So we're going to kind of do the same thing. I'm telling you that these are all rose curves. So right away, you can kind of see the differences between the circles and the rose curves. Notice now with a rose curve, you have a number in front of the theta. So you have that coefficient on theta. And I want you to go ahead. You're going to kind of do these very similarly in your calculator. So you're going to get y equals, let me clear that circle out of there. And if I was to type 2 cosine 3 theta right in there and graph it. Oh, that looks a little bit small. Let me zoom in. So I'm going to go ahead and zoom in. Okay. Oh, look how pretty that is. So that's what we call a rose curve. And each one of these is actually called a petal. Okay, so just like a flower has a petal. And so if I was to sketch that, and I know my graph doesn't have to be perfect, okay, but that one's floating over there. Now, each one of these petals is supposed to be congruent. I know my graph isn't exactly perfect, but these are all supposed to be the same size. And it does get a little bit distorted on your calculator. Again, zooming, and if you hit zoom square, sometimes it makes it look a little more accurate on there so that you don't get that distortion. So this is a rose. This has 3 petals. And if you look carefully right here, I wonder if I can even zoom in one more time. So if you zoom in, oh, that's too far. I was going to try to figure out how long that petal is. So let me zoom out. So it looks to me, you can't really tell how long these petals are, but on this petal here, it looks like this is a petal of length 2. So this would be a rose curve with 3 petals. Each petal is of length 2. That's how you would describe that. So what I'd like you to do now is pause the video, go ahead and graph these using your calculator. Again, you're in polar mode still. And then see if you can make some conclusions about, try to fill in these blanks. See if you can kind of draw those conclusions. So go ahead and pause. Okay, hopefully you've got some graphs that kind of looked like this. I know this one's got a little crazy. So here we have, this is a rose curve. It has 3 petals of length 3. Here, this rose curve has 8 petals, and they were of length 2. Okay, here there was 4 petals of length 3. Here there was 5 petals of length 3. So, and that was 2, 3. Okay. So, what can we kind of conclude from this? So, cosine graphs, rose petals, you know that it's going to be a rose curve if you have a number in front of that theta. Notice that if you didn't have a number in front of the theta, you would get a circle. That's the ones we did previously. So a number or a coefficient with that theta is what's going to turn it into a rose curve. Notice there's no plus or minus signs here. Everything's attached by multiplication. So you've got that. And the graphs themselves, the cosine graphs, look like they have a petal cut in half by the x-axis, okay? So notice this cosine curve. See how this has a petal cut in half by the x? This is a sine curve. This is a cosine curve, and it has a petal that's cut in half by the x-axis. Sine curve. Cosine curve. This time the petal that's cut in half by the x-axis is over here. So cosine graphs will have a petal cut in half by the x-axis, whether the number of petals is even or odd. So here, even though this was an odd number of petals, right, it still had it cut in half by the x. Odd number of petals cut in half by the x. Even number of petals cut in half by the x. Okay? Where with a sine curve, okay, they will, they'll be cut in half by the x-axis if n is odd. Okay? So where n, that's that number in front. So when n was an odd number, see how here it was a 3, this was down here. but when n was even, they kind of floated between, okay? So that's what we've got there. And notice that the number of petals, if n was an even integer, so if n was even like here or here, you had to double this number. That corresponds with the number of petals. So the rose will have 2n petals of length a. So that number in front was the length of the petal. And if n was an odd integer, like here, the rose will have exactly that number of petals, and they will still be of that length, a. Okay. Notice that over here, this negative in front, like where normally the cosine has the petal cut in half by the x-axis on the right-hand side, okay, on the right-hand side, when it was negative, that kind of flipped over here. I bet you if you graphed this one without the negative, the petal that would have been cut in half was over here. So that's how that's going to change it. And that's what we have for rose curves. All right, the last type of polar graph that we're going to be talking about today is called a limison. And basically, there's a few different categories within these. So you'll notice that the setup to kind of get these types of curves, notice that there's no more multiplication, right? Now I have either plus or minus signs between them. Okay, so they kind of have this general form here. Okay, and what's going to be really important is looking at the ratio between these two numbers. In other words, this number divided by that number. We call this number the A and this number B. So you're going to want to look and compare what happens when you divide A divided by B. What happens when that number is between 0 and 1? What happens when that number equals 1? And what happens when that number is greater than 1? So we're going to use the calculator again. So I still got those rose curves in there. So I'm just going to type in 1 plus 3 sine theta. Type that in there, and then I'm going to graph it. Oh, I'm still zoomed in. Well, let me just do a standard window there. Oh, okay. I'm going to adjust this window by hand. I'm going to make my x's there, and I don't need to see so much below the x-axis, but I want to see a little bit above there. Let's just do 8. Let's see how that looks. Oh, that's a much nicer picture there. So I just kind of adjusted my windows. Now, what you'll see here is I call this a loop, okay? This is still a limison, but this is kind of the subcategory. This one kind of has a loop. So go ahead and graph the rest of these. Actually, I'll graph this one with you. So here, we'll put this here. And it kind of goes something like this, okay? So you've got that. Now, let's throw in, I'm going to work vertically down the page. So I'm going to say 2 plus 2 sine theta. We're going to graph that one. And so you'll notice this one, it doesn't have that loop. It kind of comes in and it touches the origin right there, and then it turns out it almost looks like a heart, okay? And in fact, that's going to be a special type. We call this a cardioid because it looks like a heart. Cardio, heart. That should make sense. Okay. So I've got this, and it kind of comes on, and I know your graphs aren't going to be perfect, but it kind of looks like that. You should be able to tell the difference. This one has a loop, and this one has a heart, so that's a difference there. And then the last one I'm going to graph here, it's 2. I'm just going to delete that basically out of there. So we've got that. And when I graph that one, notice this one, it doesn't have a loop. It doesn't have that heart shape. It doesn't come, but it kind of flattens out at the edge here. I might even need to adjust my window a little bit more so that you can see it properly. So instead of there, I'm just only going to go to, I probably could only go to 5. Let's see if that helps. You can tell it's kind of this flat edge there. I'm even going to adjust my x minimums. I only need that to be -5 to 5. And that does a better job. See how it kind of flattens out right there? It's not round like it is at the top here. So that almost looks like a circle, but not quite. It's not quite a circle. It kind of has this flat edge. So it's like flat, and then it's round, and then flat. So it's kind of like flat there. Okay? Oh, I did not really do a good job of drawing that. That one should be like, what is that? 1, 2, 3. And it was only 1 down. So I did a bad job of sketching that one. Okay, but go ahead, pause the video, and go ahead and sketch the rest of these.